Quite often in nanophotonics, we have to deal with diffraction gratings. They come from arrays of particles or lines, and it's interesting to see how the diffraction orders are computed, and what they mean, and how we can use them. So I'm going to explain this using symmetry as an argument. We are going to assume that everything in the response of the structure is going to be determined by the symmetry given by the grating and the incident field. So first we're going to see this using the one-dimensional case. So let's assume that we have a 1D array of particles that we have a schematic on the right here, and the periodicity of this array is L, that is the distance between centers of our particles. In the same way, we have an incident field for which the k vector is named beta here. And we can define the we can define the incident field this way, that is, the intensity at a point anywhere that is defined by the vector R here is going to be this complex exponential, which includes the k vector, and here I have separated both terms. When you look at this and you try to apply this formula at L compared to at this location, we get what is called the block conditions. That is that the value of a field at x plus L is equal to the value of this field at x, but it is shifted by a phase term that is going to combine the parallel component of the k vector on this distance here. And our assumption here is that every field in the problem is going to have to obey this block condition, because, well, it only makes sense that what happens at one point here is basically exactly the same as what happens over there, and so on. This is a symmetry argument, except that since our incident field is tilted, we are going to have a difference in, let's say, the time response between this particle here and this one. So this difference in time is translated into a difference in phase when you look at the permanent problem. Okay? Now, we say that any field inside this problem is going to obey a similar equation, that is going, so let's say we have a field in the xz plane, so we can say that this is an amplitude that is a function of z multiplied by a complex exponential which contains the parallel k vector of this field multiplied by the x coordinate. Now, if we take the block conditions that we just defined and we try to apply it to this, so let's say we take this formula and we apply it to x plus L, we get something that looks very similar to the block conditions that we had before, except that in this case we have the kx value over here, and we want it to obey the block conditions, so we have an equality between those two terms. Now, we have, in this case, the equality between the exponentials, but that doesn't mean we have the equality between the terms inside, because there is the problem of the rotation around the complex circle. But that means that those two terms are equal, but up to a certain number of 2 pi rotations. So we have kxl is equal to beta xl plus 2 pi times n being some integer, that is positive or negative or 0, which means that the kx value, that is the parallel component of the output k vector is equal to the parallel component of the input k vector plus a term that is related to the grating, and this is basically called the Bragg formula of gratings applied to the one-dimensional case. And now that means that the full field inside the problem can be written as a sum over all those terms, so over n, and each of those terms is going to have its specific amplitude along z. And we can see here that basically the field inside the grating is going to be a Fourier series of Fourier series in itself, so it can be expanded into Fourier series. Okay, now let's look at the 2D case. So now this is the top view of the problem in this case. So the grating itself is defined in the xy plane, and it is defined through two vectors, so A1 and A2, which are going to define the basic cell of this grating. Again, we have an incident field. Here we only show the parallel components of the k vector. So now this is in 2D. We represent this as a vector itself. Again, we can define the incident field using a complex exponential, and I've separated the parallel and perpendicular components of the k vector. And we can, once again, try to figure out the block conditions, except that we are going to inject the vectors A1 and A2 inside this formula on the left, and we are going to get our two block conditions that our field will need to obey next. Okay. Now, we again want our field inside the electromagnetic problem to look like this. So it's going to be an amplitude along Z and multiplied by the complex exponential containing the parallel k vector, the output parallel k vector times the location. Just like before, we take this and we apply the block conditions. So we have two equations. And again, we have equalities between exponential terms, which of course translate again into equalities of the terms inside plus a 2π shift. That is going to be very important. In this case, I've kept everything as a dot product because we are going to use this to get the full solution right now. But to do this, I first need to define some kind of coordinate transformation. So let's say we have vector v in the xy plane, and we have, of course, our two vectors defining the grating. We can take the dot product of v along those two vectors, and if we expand it, we get two equations that contains the different components of each vector multiplied with each other. But when we do this, we actually have a system of two equations with two unknowns inside. So that means we can invert this system to obtain Vx and Vy based on everything else in the problem. So when you do this, you get those two expressions. So we have Vx and Vy depending on the components of the A vectors and the dot products between V and A1 and V and A2. And when you look at this expression, you can basically rewrite this using dot products and cross products between the components and the Z vector, which is perpendicular to our grating. So this is very important. Now, so this gets a bit more complicated. When we have defined this for any vector that is inside the xy plane, which is also the case of the parallel components of the k vector of our output field. And when we apply this, so we apply these stuffs, which means that we get the dot products inside this expression. But when we look back at our block conditions, we have dot products here, which means that we can put inside the full equation those terms, which is what we have here. So I've replaced those dot products with their other expression. And instantly we recognize, well, instantly, when we move terms around, we can recognize basically exactly the same equation as for V, but this time we have the beta parallel, which has been expanded, and we can pull it out of this and have it outside on a remaining term, which is going to contain the cross products on the p and q integers. And in this, we can actually recognize those two expressions, which are very common, which are the expressions of the reciprocal vectors of the lattice. And when you combine everything, you get the Bragg formula for the 2D grating, which is in this case written in vector form, with G being a vector of the reciprocal lattice of the grating, and G is just P B1 plus Q B2, and P and Q are integers, which can have a positive or negative value. So once again, we have the output parallel K vector being the input parallel beta vector plus a term of the reciprocal lattice. So this is exactly the same thing as for the 1D grating, but in 2D in this case. Also, when you look at this in the 2D plane in the K space, so this is a space that is defined along Kx and Ky, you can now see that the diffraction orders are going to be points inside this space. This space is going to be shifted by the parallel beta vector. So this space itself is defined by any point of the reciprocal lattice, which is why we have now between 2 points, we have either B1 or B2. And this is the reciprocal space. Okay. Usually, when you do some diffraction with a laser of a grating, you are going to see this appear because, well, you just image the reciprocal space, and you are going to see the diffraction orders. And when you plot them in the reciprocal space, this is exactly this. One thing that is important to understand is that there is, while I've represented only a few of them, there is an infinite number of orders, just like for the 1D case, n goes up to infinity, and those orders at infinity are evanescent. And just like for the 1D situation, we basically have a Fourier series. The field itself expands in a Fourier series, except it's along some strange vectors. Okay, so what does this imply? When you, so let's say that you have a grating that is, well, it doesn't matter its shape, but you illuminate it at normal incidence. So at normal incidence, the 0, 0 diffraction order is going to be at the center of the K space. and everything else is going to be around it according to the B1 and B2 vectors. When you change the incidence, actually what you're doing is that you are adding the beta parallel vector like we saw before, and that means that when you are using a different incidence, you are only shifting the diffraction pattern in the k-space. You're never going to rotate this pattern around the axis. You're only going to shift it according to the parallel components of your incident k vector. So if you see that things have rotated, that means there is something else going on. Most likely you have rotated the grating itself, and not the you have not changed the incidence. Now, let's say we have an actual grating, and above this grating we have a refractive index N1, and below this grating we have the refractive index N2. Okay, so N1 is going to be the superstrate, and N2 the substrate. We know that in any medium we need to have this equation that is obeyed, that is the three components of the k vector are going to be related based on this, that is the k0, that is the k in free space, multiply by the refractive index, you square everything, and you have this equation. But now this means that the perpendicular component of the k vector is going to be written as a square root of all this stuff. Now, we have seen that the parallel components of the k vector can be basically anything, because they can be any point inside the reciprocal lattice, and this goes up to infinity. That means that this term inside the square root can be very, very negative, which implies that the perpendicular component of the k vector can be imaginary. And so when you draw basically k0 times the refractive index on the k-space, you're going to get those circles. What they mean is that inside those circles you're going to have propagative diffraction orders, and outside those circles you're going to have evanescent diffraction orders. So let's look for instance at N1. So N1 translates into K1. When I multiply K0 by N1, I'm going to get K1. You draw this, you have a circle, and you see that in this case, in the medium of refractive index N1, you are only going to get 4 propagative diffraction orders. Everything else is going to be evanescent. Inside the substrate, for instance, since, let's say, we have a higher refractive index, we are going to have more diffraction orders because the circle is bigger here. And of course, in both cases, we have an infinite number of evanescent orders, and they are going to participate to the near field on the grating when you're not looking directly at the structure. But if you are a bit above or a bit below your structures, the evanescent field is going to be defined based on all the evanescent orders outside those circles. Okay? Now, let's say we want to couple our grating to something. So let's say we have targets. So this target can come from something else. It can be we want to couple to a plasmon, want to couple to guided modes or something. One way to do it is that we can design our grating so that the target matches one of the orders of the grating. So this is what I've represented here. So in this case, we have made the grating so that both end up at the same point. But if you can't really do it, or if for any reason they don't match, you can. So let's say you have the grating just like before, but this time we have a K target that has to be away from any of those points. You can shift it. You can shift the full diffraction pattern through the incidence. So this is what is done usually with the Kretschmann configuration. When you give an angle of incidence to your field, what you're actually doing is that you're matching in this case, the 0-0 order with the K target of your plasma. Of course, this stuff doesn't only have to work with propagative orders, it can work with evanescent orders, which is exactly the Kretschmann configuration, because we are matching the 0-0 order in the Kretschmann configuration with the K of the plasmon. And this is why it works, this is why we have coupling. Let's look at an example, for instance. So this comes from FTD simulations. In this case, we have a waveguide of 200 nanometers of index 3, and on top of this, there is a grating with a periodicity of 180 nanometers. And when you compute the response of this stuff, you see sharp peaks inside. And actually, those peaks, they come from the diffraction orders, the evanescent diffraction orders in this case. And we can match them to their values. So when you look at everything, you can find that this one can be exactly computed as the TM0 mode, and this one can be computed as the TM1 mode, and you're going to see their signature inside your spectra. In the same way, we can look at plasmons, for instance. So in this case, I've taken 50 nanometers of aluminum on top of glass, so it's going to be opaque, light is not going to go through the aluminum. If we look at a wavelength of 500 nanometers, when you compute the wavelength of the plasmon for this case, that is 50 nanometers of aluminum, you see that you need to have a matching periodicity of 490 nanometers, and this is what I've represented here. So in those three figures, this is the field computed based on a grating, on a finite grating. That is, in this case, I have only one cell, so only one particle around. So this particle couples a little bit of field along the surface. In this case, we have, I think, 3 of them. So I only show one, but there is another one here. And those 3 contribute to coupling to the aluminum surface, and we see the field that has propagated here. And in this case, I have 10 periods, and they couple even better than before, so that's why we have a stronger field along the surface here. And when you look at the spectra, you're going to see this coupling in this case. So this is computed for perfectly periodic grating, and we see the signature of the plasmon coupling in this case.